thank all our speakers and for being with us today. And I hope you know, this is a pleasant experiences and we can continue doing this. So now I will pass, you know, the control to Raviv. You muted.
Thanks, Helen, and welcome, Vishal Khandelwal. I hope. I apologize for mispronouncing, I guess.
No, you got it
So,
right.
okay, great. So, Vishal leads the physical optimization team for the digital implementation products at Synopsys. He has 15 years of R&D experience in building state-of-the-art optimization engine and PNR flows targeting advanced node, low power, high performance design. More recently, he has been looking at bringing machine learning paradigm into digital implementation tools to improve power, performance, area, and productivity. Perfectly matched to our MLCAD. Vishal has BTech from IIT Kanpur and a PhD from University of Maryland. He has co-authored several patents and over 20 publications, and I'm welcome Vishal for our plenary talk on machine learning enabled next generation physical design and EDA perspective. Welcome, and all yours.
Thank you so much, Aviv. It's great to be here. Thank you, everyone. I'm glad to have the opportunity to present in this forum. Let me just get my slides in order. Can you see the slides or you don't?
Yes, we can.
Okay.
Yes. And now it's full screen, so you can go.
Okay, just give me 1 sec. I think something's not quite right. Sorry, just, okay, I think I'm good to go. Okay, so, you know, we've heard some great talks earlier this week, even this morning from Elias. So I'm hoping to add some more color from an EDA perspective. You know, my team and I have been working on machine learning and physical design flows for a couple of years now. So we've had some experience both from a development perspective as well as productization perspective. I think productization is an important aspect because if you really cannot make your technology fly at a design company across a group of designers and they don't come back and tell you they see value, it's always questionable if what you're doing really, you know, adds value. So we'll share some color on that. The agenda for the talk is quite simple. You know, I really want to start by motivating why physical design needs machine learning. I want to touch upon a few enablement issues because I think, as I said, productization is key. So we need to touch upon what does it take to really productize ML features at a semiconductor design company. And then I'll share some of the ML work we've been doing both in the tool and around the tool, and then I'll have a short summary at the end. So really the big picture for physical design is that, you know, physical design really is an ensemble of NP-hard problems. And if you really look at most of these problems, you know, it's not even possible to formulate an exact solution for most of them unless you make, you know, fairly simplifying assumptions. You know, Moore's law, process node scaling has just made things harder and harder, bigger and bigger, complex and complex. So it's not been any easy in the past few years. So an EDA tool for physical design really is a system of what I would call complex and sophisticated algorithms that really try to target best-in-class PPA, because that's really what every designer wants to see. But at the same time, the turnaround time is a very important aspect of a physical design tool. And you have to think of this from the point of view of a designer. At the end of the day, when a chip is being designed, the time to market is a very, very critical component, right? We see that across, you know, mobile, across pretty much any generation of semiconductors, there is a yearly cadence now to actually getting your products out. We are way beyond the times when, you know, a new CPU generation took 3 to 4 years to develop. So if you really need to hit yearly cadence, you need your tools to be delivering PPA with very, very good runtime. So these are some of the, grassroots realities for EDA tools. At the same time, capacity and complexity has just kept pushing us harder and harder, right? Today, I would say 3 to 5 million instance flat block, right? I'm not talking hierarchical, I'm really talking flat, is very common. And if you look at sign-off complexities, most design companies are probably signing off at 15 to 20 to 30 corners. So now when you put it all together and think about the amount of compute and complexity that a very typical EDA tool is dealing with, it's very, very high. And these are some of the challenges that we need to keep in mind when we try to bring ML into the flows. Okay, so I'll add a little bit more, and what exactly is the ground reality? We have this very simplified flow view of what place and route tool is, but I mean, there's a lot that goes behind it. I mean, routing has become incredibly complex. DFM, metal fill, TPT, DPT, all kinds of rules. Every week we get new rules to add to the tool. Think about placement rules. All kinds of complex spacing rules, filler rules, implant rules, MV rules. It's just, everything keeps increasing. Cell architectures, right? We went to FinFETs, we're talking gate all around now. You have wide cells, tall cells, you have all kinds of pin access complexity that you need to model. And it just keeps going. Static timing analysis, just this component, variation analysis, SI modeling, and just moments, LVF. It's just incredible amount of complexity that keeps coming into the problem statement. Similarly, power, right? Low voltage, so pretty much low VDD design has become very standard. Glitch power is starting to become very important. So to get all of these effects modeled into an implementation flow, it just makes things harder and harder. And of course, EM, right? Cell EM, clock EM, signal EM, via pillars. It just keeps growing. So this slide really, I was trying to kind of lay out the ground reality of what a PD tool deals with. Now, the interesting part is some of the more esoteric requirements are under NDA. I cannot even mention them on this slide, but when you really bring all of those in and you really try to absorb the complexity of the problem. In this picture, I would request everybody to think for a few seconds about something as simple as a gate sizing problem. And people talk about optimality and how to solve things optimally. Don't cut corners to save runtime. But when you even think about something as simple as gate sizing in the context of all the details you need to deal with, thinking about optimality feels kind of like a dream at the moment, right? You have to have very intelligent algorithms who are able to model and predict all of these and really give you a good high quality solution in reasonable runtime. Now, modeling, prediction, all of these are words that directly makes you think that ML should fit right in. And that's really the point. Now we've reached a stage where traditional algorithms are really splitting at the seams, and you need that extra oomph to come in from ML. And that's where all the modeling and prediction opportunities in ML come in. Another way to see what I'm trying to say is, think about Moore's law. A very common way to look at Moore's law now is you try to look at the performance per watt curve. And every new process node, let me try to get a pointer. Every new process node, foundries are claiming that they're pushing this higher and higher and higher. Hard reality is that, when you implement the design, when you realize the design, you're always behind the curve. And it's a constant problem. This PPA gap is a constant problem that we in EDA are fighting every single day, because people expect us to really bridge the PPA gap. And it is indeed true that in EDA, we are constantly investing in improving our algorithms and flows, right? The goal is to close this gap. So, we haven't taken our feet off the pedal at all. But it's very clear to me and to many of us at Synopsys that there is no way to just close the gap. You really do need ML enabled tools to close the gap. So, in my mind, ML in physical design is a necessity. It's not just a desire, or It's very real. We need it, and many of us are working towards this. Okay, in the next few slides, I want to touch upon some very, very basic things, but I think they're important to think about when you think of it, how to bring ML into EDA. What kind of learning models to use? Supervised, unsupervised, and RL are very common paradigms. We've heard some great talks about, at least RL and supervised learning in the last few days. My personal experience is clearly supervised learning is ahead in terms of adoption. It's popular because a lot of the problem statements we come up with are, generally speaking, prediction, look ahead kind of problem statements. A lot of the prediction data or the label data is available. It's not very hard to get label data in a physical design flow for many of these problem statements. So, the challenge really is you just need to focus and have very solid feature engineering. So if you have labeled data, you have a good problem statement, really the unknown part is feature engineering, and you do some magic there and you can fairly easily come up with a model that works. Unsupervised learning, it's seen limited usage. I've seen people are generally leaning towards supervised learning in most cases. I think this morning in the keynote, Elias pointed out that it's kind of like a underexplored area in some sense, and hopefully in the future we'll see more, more usage of unsupervised learning in EDA. Reinforcement learning certainly is the buzzword. Clearly a lot of academic research is focused on RL. For me, the biggest value add, or the biggest reason I am excited about RL, is that it really has the potential to push your PPA to the next stage, because supervised learning essentially is just saying the best you can do is whatever your labels are. But who really says how good your labels are, how optimal your labels are? Yes, you can predict congestion, you can predict timing, you can predict many things, but your labels may be suboptimal to begin with. So really all you're going to end up doing is predict perfectly to suboptimal labels, right? So there's no guarantee that you are really any closer. Well, you're probably closer to the real optimal, but you may still be very far. Reinforcement learning, on the other hand, has the potential to go above and beyond. So that's a very exciting opportunity in my mind. We've done some early work in RL. This year we took something as simple as a gate sizing problem, and we've tried to use RL to prove that how much is the gap. And we do see that RL sizing can really beat the state-of-the-art sizing engines. And state-of-the-art here literally means, now, I can tell you, I own the optimization team. We are very proud of our algorithms. We really feel they perform well. So when we beat it, it's a big deal for us. But we've had some learnings with RL. It is definitely compute heavy. When you're trying to apply RL on a 5 million instance block, there is a lot of compute involved there. Transfer learning comes in. Yes, all of that helps. But there is still a long way to go to really prove, what's the right level of abstraction to really make RL a reality in a place and route tool. So there's a lot of opportunity here for, R&D and, really explore some ideas and actually collaborate and try and get something done. Another very critical component of machine learning is, training data. I think it's one of the things that we maybe sometimes take for granted, but you have to ask a question: where do you get your training data? We at Synopsys have access to many designs, so I would say compared to academia, we are definitely in a much better situation. But fact of the matter is, even we don't have access to all the data we need. There's still a lot of data that is proprietary. We cannot see it or touch it, and that makes it tricky, because if you're training models with the data we have access to, you don't really have all the design process and library data, especially the latest generation. Typically the access we have is kind of like half a generation or one generation behind. So we are close, but not quite there. The other way to get training data is on-site. You really build an ML platform which can continuously harness and manage the training data. And that gives you access to real design process library that a designer is using for that project. And really, you have the best quality training data. Um, there are some interesting implications here, legal implications. And who owns this IP? When you build an ML model, you have to view it as an IP. Who owns it? And that's always an interesting question. And I'm very far from a legal person, but my rule of thumb over the years is anything we train in-house is our IP. Anything that is trained on-site is absolutely customer IP. So, there are all these implications, and, we have to factor all of this in. So when we make a choice that am I gonna build a model with in-house data or on-site data, you have to think about all of these aspects. A related question is then, what is your model training strategy? Because depending on the data and what you're going for, you have to choose your model training strategy. The ideal and preferred solution is always pre-trained, right? We pre-train the models with the data we have, we ship it with a tool, it's easy to use. What's the downside? Downside is that, if you really believe your model needs features which are very specific to the design or the process or the library that it's going to work on, then, pre-training your model is always going to be a little bit behind. So you are compromising on accuracy. A second balanced paradigm is, we have been able to build what we call on-the-fly training models. Now, so what happens is now when the tool is running at the customer site on the customer block, the tool under the hood can generate data and train and use the model. It's great because you are really, you get access to the right data. You can build models which are really tuned to the block you're running on and push PPA. What's the downside? Downside is that you're eating this training runtime in every run. And as I said, runtime is important. So it's very difficult to build heavy models, for, if I may say, or, deep learning models, which often need a lot of data and, have, depending on the model and what you're doing, it can have fairly large training runtimes. You really cannot do that on the fly. So here, this is most suited for lightweight models, often tree models, which you can train fairly quickly with small amounts of data. And of course, the third one is offline training. That's really where deep learning, sits, because you can really have a ML platform which is harvesting data across, many runs, and then you have a dedicated online training flow, and you train a model and you deploy it. The goal typically for offline training, I should say, the expectation from customers for offline training is you train a model that works across the project. So, you may have 20, 30, 40, 80 blocks on an SOC. The model you're training really needs to scale across all those blocks. So these are some very real, very practical challenges that, we in EDA will, have to address when we think about ML deployment. Another, very simple slide. When you think about ML enabled tool flows, there are really, from an R&D perspective, there are two aspects, right? Where are you going to get your data, your strategy for model training, and the compute you have. In some sense, model training is somewhat dependent on compute. But there is another very critical component. Once you have a model that really performs and is giving you the accuracy you need, integrating it in a complex place and route tool is a very, very huge task, because really you need to integrate it and drive consistent, robust convergence, which means that if I take my ML feature and I really run it on K blocks, it shouldn't be that half of them improve and the other half degrade. And that never flies. So taking, these complex, highly tuned, highly sophisticated algorithms, bringing in an ML model to add some knowledge and really drive meaningful convergence has proved, at least to us, has proved to be a pretty hard problem. And a lot of our time actually goes in these two areas when we really develop an ML feature. So it's something to keep in mind. This is just a very, a very crude abstract of, if you really want, ML to productize, you need to have an ML platform built into your tool, or really running alongside your tool. You have to have an ETL pipeline which is quickly pulling out data, very seamlessly, very efficiently, from your flow when it's running, right? And you have a data store and you have APIs. The APIs can be used to do analytics and visualization, which feeds back into the tool. And you need to somehow be able to plug into a distributed compute, right? It could be an on-prem cloud or a AWS cloud or a Google cloud, but you need this platform, so to say, to be there. And you really need to think about multi-user, multi-block, and continuous data, support here. So these platforms are critical because once you get all of these details right, that's really when you can say that you truly have an ML enabled PD flow. Okay, changing gears, I want to talk a little bit about what we've been doing at Synopsys. So at Synopsys, we've had multiple years of investment in both ML in the tool and ML around the tool. And ML in the tool really means that generally speaking, we target PPA and trying to improve convergence and runtime. We see opportunities for ML in optimization, in prediction, to use as classifiers, to use as schedulers. Schedulers is an interesting one, right? When you're really doing distributed compute and you're partitioning your design problem, and say for every partition you have a choice of algorithm, which algorithm should run on which partition, because you can have K algorithms that can apply to a partition. How to get the overall best throughput from that distributed compute framework while getting the best quality of result as well. There is an ML problem there. So we've really done some work in that space too. The other half is more focused towards ML around the tool, which is really targeting productivity in most cases. I will touch upon, design parameter optimization. We have some interesting work there. We have a lot of ongoing work in being able to develop what we call AI apps around the tool or around the platform, which really go into, debugging, prescriptive solutions, and improving the general productivity from a designer perspective. So our vision really is that we believe, a self-optimizing design tool should really be able to learn on real designs, right? And it's a combination of pre-training from, early data or self-training from previous part of the flow or on the fly, or, self-training from previous runs. And once you have this learning, we really want to accelerate PPA. And it comes through, basically a combination of predictors, optimizers, classifiers, schedulers, depending on what you're going for. There is opportunity to apply ML models in many, many ways. This is a slide that really tells us, forget the marketing part of it. I'm not trying to market any Synopsys products here, right? I'm really trying to convey a technical point, which is that, we've really taken a very hard look across the entire PNR flow. This flow chart is a very simple way to think about how place and route works, right? And starting all the way from synthesis through sign off. And we've taken a hard look at where in this flow is an opportunity to do something with ML, right? You can think of, structural congestion optimization. Very, very early in your synthesis, you're making a lot of mapping choices which affect area congestion timing. And you don't really have a very good idea of what that part of the logic cone is going to end up being, either on timing or on congestion. So anything that you can do there to predict which cone of logic goes to what architecture is a big win, right? Similarly, we see a lot of opportunity in floor planning and macro placement, right? So we have some features showing very good, results there. DRC prediction has been spoken about, right? We know at advanced nodes, global route, detailed route, the general correlation is sort of weak. There is a need to predict detailed route DRC early in the flow so that you can mitigate it. A lot of work has been done in this space. I think there was a paper earlier in the week in that space as well. I have a slide on that. We've done some interesting work there, and I want to share some data there. Smart reference flows, right? We spoke to. I think Ismail spoke about this as well, where instead of having a static tool flow, what you really want is an intelligent tool flow. We call it smart reference flow, where as the tool is running, it's collecting data, it's applying models, and it's detecting what kind of a design am I running. And on the fly, you're changing features, knobs, turning things on and off to really drive in a very automated way better PPA and convergence. So this is reality. We have a lot of work here too. It's showing interesting results. IR prediction and optimization, the general problem of timing prediction. This, I believe, is a huge opportunity. Pick any box on this flowchart and you can define a very, very meaningful timing prediction problem. And if you can kind of get it right, there is PPA there. So we've focused quite a bit on the timing prediction part. And of course, in sign off, right? The goal is always, we spend a very typical design cycle spends a lot of, actual time in ECO and sign off. And that's where anything you can do to bring ML and speed up, PBA analysis or do ECO faster, huge value there. Okay. I'm trying to keep track of time. So the very simple flowchart for PNR, again, we are constantly trying to blur the boundaries, right? We want synthesis to be aware of placement. We want placement to be aware of clock to be aware of routing. So, this is what we do all the time, day in and day out. And the goal is to eliminate surprises, because every one of these, back loops is an expensive loop. And the worst case scenario is, you go all the way to sign off and you realize your design is busted. And you really need to loop all the way back, tweak your RTL or tweak your floor plan and spin all over it again, right? So a lot of opportunity here. Every component wants to know what is going to happen later. So all of this translates to a lot of opportunity for ML-based prediction. Okay, I'll switch gears into some of the work that we've done. And I really want to emphasize we've productized, because over the years, to be honest, we've explored many ideas, we've prototyped many ideas. Hard reality is, if I say how much have we productized, it's a humbling percentage of the overall work we've done. And that's where some of these productization challenges come in. But one of the things that has done really well is timing prediction. It's a very valid problem, right? One thing we focused on was to improve CTS and post-CTS optimization by predicting post-route timing. And this is a huge correlation problem at advanced nodes. There's just so many complex effects, routing rules, advanced timer models. There's so many things that just cause this timing correlation to be very poor. And why does it matter, right? When you have engines like, global placement or, global skewing, these engines are really feeding off global timing. If you don't have a good sense for your global timing, the trade-offs you're making here could be hurting you or leaving quality on the table, right? Both happen. And it's very late in post-route to really fix many of these issues. So the sooner you can align your timing or improve your timing correlation, the better your convergence and PPA is. So we've done some interesting work here. We see very high accuracies with our model. We have a tree-based solution here, which trains on data from early runs. Again, a lot of the effort in this work really went into integrating the model and making sure we can drive convergent PPA closure, which moves the needle. Because the other thing we realized is every time we go out and we tell anybody, hey, we have a new ML feature, it works really well, we realize the expectation and the bar is very, very high. Any ML feature is not judged the same way as any other new algorithm that we would go out and try and launch. So the bar is high, and we've had to struggle with some of that. But we've seen a lot of good success just sharing one data point, and we have many. It's a real data point. These are tape out blocks which deployed with our features. We see very significant improvements in timing. We see improvements in power. We often see improvements in runtime. Right? And we didn't really target runtime. This really is trying to target PPA, but what we see is you improve convergence, you improve runtime. So it's a win-win. Another interesting work is DRC prediction. Many people have spoken of it, right? You want to be able to predict detailed route DRC early in the flow. You want to plug it into placement, which also is an interesting topic. I'll add a few words on that, but you really want to do something good with it. We've explored this for about maybe 3-4 years now. We've gone through a few generations of models. We started with something very simple, SVMs. We went to deep learning. We've tried CNNs to make it into an image problem. We've tried to predict classified DRC, so we can predict both the occurrence and intensity of DRC, so that how much DRC is happening where. So, a lot of good stuff. The modeling part, really worked well most of the time. Integrating it in the tool and driving better DRC convergence is a harder problem, right? What we've succeeded in very nicely is doing what we call pin access optimization, because at advanced nodes, one of the big things is getting your pin access problems right. A lot of the DRCs that happen late stage is really related to complexity of pin access. And for the better of the worse, our global route engines are not really up to speed when it comes to modeling all of the nitty-gritty details related to pin access. That's again an opportunity for EDA researchers, that how can you make global route really model all of these advanced detailed effects. Um, so what we've done is, we really integrated it in the pin access problem. We have an engine in our legalization, or what we call detail placement, which can do very targeted surgical fixing for pin access problems. So what we do is we use the ML model to predict where the problem is, localize the problems, and then we get this engine to go work in that region. And it does very targeted fixing, because if you try to fix the entire layout for pin access, the amount of displacement and perturbance you do is a lot, and it hurts your convergence. So the idea here really was keep it very focused, very targeted, go in and solve your problems. And it actually works. It's working pretty well. We have many data points now which show that it's very effective in reducing really M1 to M3, so the lower layer pin access problems, and it translates to improved PPA convergence because you're not perturbing the design as much, and you get improved routability. So this feature seems to be doing pretty well. A comment I want to add is about, everybody says, take this model back, plug it into global placement. I think it's a very valid problem statement. We are working on it. We had some interesting observations there that, global route really serves two purposes. One, of course, is making sure your design or your detailed route is going to be routable. That's absolutely a primary requirement. A secondary requirement is also easing the life of router. DR should get an easier problem to solve in. So when placer comes in to alleviate congestion, it's trying to give an easier problem to basically routing, because there is a very large gray area where the router can always come back and give you a fully routable solution, but it did that after a lot of grinding and adding wire length and adding timing and power, so it doesn't help overall PPA. So really from a placement perspective, what we see is that any model that's predicting only detailed route DRC can only augment the way general congestion is being modeled today. So that's really the direction. So if you're thinking about taking your model and plugging it into a placement engine and making it produce better results, try to think about that aspect. How do you augment and not replace what you're doing today? All right, I'm going to keep going. Some more interesting problem statements. We worked on mux congestion optimization. This really is the early synthesis problem, right? There's a lot of designs which have structural congestion. When you have, select ops that you're trying to map, there's always a trade-off in what architecture you pick. And there's a very stiff area trade-off. If you go completely area driven, you can really save area, but you risk congestion. If you were always trying to be conservative on congestion, then you give up a lot of area up front, and it's an area bloat you give very early in the flow. You often don't recover it back. So this is a very classic prediction problem. We don't have enough information there. All you know is the net list. So we've built some models which are trying to predict structural congestion and drive a more intelligent optimization of select ops. And it's showing very interesting results where for a very reasonable trade-off on area, we can see pretty dramatic improvements in congestion in many cases. Macro placement, again, this is not RL. We've talked about RL macro placement from Google. So this approach really is not RL. It's a pre-trained model combined with on-the-fly training. So it's an interesting concept. And its goal really is to drive better exploration of macro placement by really predicting congestion and timing. And we are seeing some very, very interesting results with this approach. it's real, it's almost productized at this point. Another general problem statement is what I call transform prediction. All of physical optimization is about identifying a logic cone, deciding how to optimize it for area or power or timing, right? Depending on what you're doing at that point in the flow. And there's always a problem for, trying to pick a better solution or trying to pick the same solution faster. So you can, maintain your quality, improve your runtime, or improve your quality, maintain your runtime. And we see a lot of opportunity here for ML because we do this millions of times during the flow. On a real big design, this operation is done repeatedly. There's an opportunity to learn from previous runs. There's an opportunity to learn from the same run and apply that to accelerate PPA and runtime. So it's also something that we are working on, pretty actively. Quickly to touch upon a couple of sign-off technologies, right? Sign-off today, really, for most design companies, I would say they do path-based analysis. And PBA compared to GBA is slow. If you do exhaustive PBA, which is what many people use, it's even slower. At the same time, ECO loops are important, both from the point of view of timing as well as power recovery. A lot of design cycle runtime goes into what we call the ECO phase. So anything you can do to speed up ECO has tremendous value. And we've seen a lot of opportunity here. In this case, it's about ECO power recovery, where we are running all this expensive PBA timing based power recovery, and anything you can do to reuse that learning from previous moves and apply it to the next few moves and speed it up is very valuable. So we have some technologies here. They're showing great speed ups in real in real customer test cases. It looks very promising again. PBA timing, classic sign off problem. How do you accelerate exhaustive PBA? And exhaustive PBA, really, a lot of the work it does is it's doing path enumeration and it's pruning, right? The goal is how quickly can I predict which path is truly going to be critical. And that's where a lot of the runtime is spent. So we've done some interesting work where we use ML predictors to really prune paths very quickly while keeping our accuracy. It's showing very good, runtime gains. So there's a lot of work going on in the sign-off space as well, primarily focusing on keeping your quality, speed up the runtime. Okay, one more paradigm. I think this is very interesting work. One more thing I want to cover is what I call ML around the tool. We've had some earlier speakers talk about design space exploration, how you can do parameter tuning. There's a whole bunch of PPA left on the table because it's a very complex solution space. We really don't know how to efficiently traverse it and get to the right solutions. So I have a slide where I'll try to kind of walk everyone through how things work today. Really, when you think about physical design, a user is sitting down with a block. You get your collateral, you get your tool settings, you get your constraints, you have some flows you've set up, and you're trying to synthesize this block. And you bring in your cell design or your libraries. You may have some choices to make there. You bring what you think is right. You bring in your technology collateral. All of this feeds into the physical design problem. And then you kind of run the tool, and the tool gives you an answer. And the answer can be viewed off in terms of PPA, right? Some timing, some power, some area. And at the end of the day, there is some expert designer sitting there who's kind of going through all this data. And he has years of experience. He has his secret sauce recipes. He's learned over the years how to get better PPA. And he's going to do all of that magic, and then he's going to go tune. He's going to tune your your tool settings, your flows, your constraints, and try and improve the results. If you're early enough in the design cycle, he may also have the flexibility to go back and tune your process, right? You can change your metal stacks, you can change your corners, you can update some collateral there as well. And again, if you're early in the design cycle, there may also be an opportunity to go change your libraries or tune your libraries, right? So the entire solution space that exists is actually very big, and there is no systematic way today to explore it. And that's where the whole DTCO concept comes in, that, if I had a way to truly systematically explore this solution space, it translates to productivity, and it often translates to better results. And you don't need an expert designer, who are actually very rare. Expert designers is not a common skill these days. So it eases the burden on many of the newer companies that don't have all the resources, that don't have a legacy of 20 years of engineering staff, so on and so forth. So what have you really done? So this is a very real problem. Everybody deals with it. And what we see is, instead of spinning over this iteration and trying to find your best result over weeks or months, what we see here really is a very ripe problem statement for reinforcement learning. And in Synopsys, we've gone and looked at this for a couple of years now. We really see it as an RL problem. You have an agent who's capable of of taking actions based on state and predict a reward. It's an entire RL problem. It needs a lot of compute, so you need to be able to be plugged into some kind of a farm or a cloud. Um, and you really need a very easy way to allow the user to specify all your inputs. So things that you were tuning, right? It's your settings, it's your constraints, process, library, hierarchy, flow. Everything should be tunable and given to the system. And the user should be able to program the intent. What are you really looking for, right? There has to be some kind of an interface, a UI, that allows the programmer to specify the intent. And then this RL system will go and do its magic, right? And what it comes out with really are very nice ways to both achieve results, explore the solution space, achieve results, and also expose some trade-offs. Because if you can really observe your trade-offs and the Pareto, all the Pareto curves, designer has a choice to decide, where do you want to operate, which library do you want to use, what area power trade-off do you want to make. A lot of this gets automated, and we have a product now. It's real, it's shipping, it's deployed at tier 1 customers. So this for me is proof of life, actually more than proof of life, of RL being reality in chip design. And I'm not going to share data. It's not supposed to be a marketing pitch. I'm really trying to share technology perspective. What we see really is that we are seeing productivity gains, where instead of a group of designers or engineers taking weeks or months to really iterate and get to that desired target PPA, now this AI system can automate that. Yes, we use a lot of compute, but we use very few engineering resource, and we can really get to that PPA very, very quickly. So this really, in my mind, is kind of game changing from an MLAI perspective in physical design. I'm right on time, I guess. Okay. So summarizing, very quick summary, we do believe physical design, really is ripe for ML and EDA, and ML has the potential to be a disruptive paradigm change. We've embraced it, from the earlier talks. We are seeing everybody in the, everyone in EDA and industry is embracing it. It's ground reality. It's definitely an area where we look forward to collaborating more with academia. So, if any of you want to reach out and try and collaborate, most welcome. Thank you.
Thank you so much, Vishal, for great talk, both the observation and the inspiring examples of the stuff that are going on in Synopsys. We have a few questions in the Slack channel, so let me start with one from Heng Wang. Thank you for a great talk, Vishal. Can you share more insight in the opportunity for applying ML or reinforcement learning in macro placement?
That's a good question, right? So, macro placement is a very interesting problem statement. I know the work from Google. Google really, in some sense, was path breaking, right? It's the first time where we saw somebody show signs of life, and we are looking into some of that work too. But in reality, it's very difficult to apply RL even, for an average customer, taking a RL engine and deploying it and applying it is very hard. What we see is when we look at how our macro placement problem works, we need very good predictors. Because what does macro placement need? You need to be able to predict some kind of congestion. You need to be able to predict timing. Ideally, you want to be able to predict power, because those are the three kind of key metrics in really deciding what is the right macro placement for your problem. And today, the way things were being done, it's not efficient because we don't have a quick way to predict timing or power or even congestion. So that exploration in a traditional macro placement algorithm is limited. What we're seeing now is if you can build very fast models, which, for example, without doing standard cell placement, right? So you've only done macro placement, you haven't done standard cell placement, can you predict congestion? Without doing any optimization, can you come up with, reasonable predictions of timing? Because what's the idea? The idea is to be able to see if two macros are talking, how critical is the logic between them? If it's, very critical, they need to be closed. If it's not critical, they can be fairly far. So you need that estimation. Power is another angle, because the interesting thing about power is power correlates with timing, right? You can get timing optimization for very small amounts of power or very large amounts of power. So knowing which logic cone is going to be power hungry when you optimize it for timing is important. So from a macro placement perspective, a lot of these decisions are made very early. And for physical design, often, we view macro placement as a fixed collateral. It's not that, late stage physical design when all of this data is available. We typically don't go around tweaking macro placement. So anything you can do in that space to improve congestion prediction, power prediction, timing prediction without having to run that actual engine has huge value for macro placement. I'm not sure if I answered that fully.
I'm sure you did. Thanks. And now for two questions from Volkan. The embedded prediction may be off and point the user in the wrong direction for improving. What countermeasure do you have?
The embedded predictions may be off and point the user in the wrong direction for improving. That's a good question, right? That's part of, if I really understand your question, to me, it translates to what I like to call tool noise, right? And the reason I call it tool noise is that a lot of estimation and predictions we do in the tool are really approximate and often wrong. And that is where I think, to be very, very honest, a lot of it is secret sauce in the tools. Over time, we have refined our algorithms and flows to minimize very gross mispredictions. Small mispredictions happen all the time. So let me take a simple example. Think of a cell and a gate sizing problem. That cell gets instantiated very early in synthesis flow, and you go through the entire place and route flow, right? On a big design, it's like 7 days. If you track how many times we go and resize the same cell, it's mind-boggling. You can go resize, just resize. I don't even mean remap or optimize or restructure, just resize. It's often dozens of times. Why? Because the context keeps changing. We just don't have the right context. We don't predict right. So if you don't predict right, the flow keeps moving, the context keeps changing, you have to be able to go back. So really the answer to your question is, all the self-correctness is built into the flow. We revisit our decisions and we try to iteratively refine them, because we really don't see a way to get it right single shot. And that's part of the reason why we have runtime challenges, because if you have to go size the same cell 10 times, that's runtime you're paying.
And I think that we are.
Thank you. I would just, this is Volkan speaking. I hope you can hear me. But just asking back to the answer, wouldn't this keep us into an eventually endless hamster loop of trying to optimize?
In practice, that's what I was trying to say, right? There's a lot of, that's what I was saying, that even though theoretically, I do believe we have errors in prediction, over time, we have built enough resilience, enough details, enough secret sauce in the tools to not oscillate, right? Otherwise, you will ping pong and oscillate. So the tool is expected to be convergent, and we do converge to a large extent. See, the other thing is, I think Andrew had some very nice data where he showed that you make a small change to the input collateral and you can end up with a totally different solution. That really is a bad sign for an EDA tool, right? If you're demonstrating that kind of sensitivity, it's a bad trend. And we internally take a lot of that seriously, and a lot of details go into making the algorithms more stable to input variances.
Okay, thank you.
And the last question also from Volkan was regarding, sorry, regarding open source EDA, especially geared towards standard physical design topics. What is your observation?
Sorry for this type of question.
No, it's a good question, right? It's something that, to be very honest, when I was, when I was a student and I was, go back 10 years, these were the kind of questions I wanted to ask too, and I've asked. So it's a valid question, right? To be very honest, I think the reality is somewhere in the middle. I think some amount of open source EDA is healthy. It's healthy for the community. It's healthy for even EDA companies, right? Because a lot of the, we are so often mentally bogged down by what I call ground reality that sometimes we don't dream enough, right? Because we're always killing the ideas because we are jumping very quickly to rationalizing them. And that's where, academia comes in play, where, the approach there is the other way. That's, simplify your assumptions, focus on the core, try and get that idea right before you worry about ground realities. There is a lot of value there. We seek that intelligence to come from academic community, right? And if we don't open source, or maybe tools is not the right word, but if you don't open source information, if you don't open source even design data, right? If you're not running the right designs, the right kind of technology, you cannot observe the problems, you're not going to be able to solve it. So I do believe that we should have some sharing. It's very hard. Often it's not even in our control. As an EDA company, we definitely have access to more information and data, but we cannot share it. Our semiconductor companies are, even paranoid is an understatement. We cannot even talk about many things, right? So sharing is very, very far. Same applies to EDA tool. At the end of the day, from Synopsys perspective, we have to be a little practical about how much we can share. We are in the business of making money. We are listed on Wall Street. I wouldn't be doing my job if I wasn't helping physical design products, do well in the market. So there's no good answer here. There's no good answer that I believe I can give to please everybody in this workshop.
Thank you, but I think your answer was also right. I mean, the open source things, they can only spur new ideas, but I don't think that they are in any way of competition with whatever is available commercially.
Right. So my approach, my personal approach is that is where, the more we can have industry and academia collaborate, right? When we collaborate, we can, we can share data, right? It's very difficult to share data in a general, widespread, uncontrolled manner. But if we start focused, targeted collaboration, we are able to share a lot of data, and we do that. So I think that's the middle ground that we need to first exploit to the fullest extent.
Yeah, you're right. Thank you.
Okay, maybe we'll push for another last question coming from Mark Wren.
Okay.
He says that DSO.ai uses RL, but RL is known to be sample inefficient. Have you considered other active learning methods that are more sample efficient?
Good question, Mark. I shouldn't be answering for DSO team. It's a different team. theme, but I think the answer here is yes. Actually, under the hood, DSO is not just RL. Let me put it that way. I think RL is definitely the biggest paradigm that DSO brings to the table, but there's a lot more going inside the tool. Different types of learning methods and strategies. It's a little tricky for me to talk a lot about that right now, but maybe we can follow up on that offline.
Great. So thanks everyone for great questions, and many thanks, Vishal, for very, very clear and inspiring and talk. I enjoyed it very much, and I'm not part of the physical design community. I come from the verification community, but it was very, very interesting and clear to me. So many thanks.
Thank you so much. Happy to be here.
Are we, oh, here we go, all the way to gathering in the beer garden, apartment, and so on, or in the bar. So see you all in a short while there. And most importantly, thanks you all for participating today, and looking forward to seeing you tomorrow in our final MLCAD 2020 day. Thank you.
Thank you. Yes,
Thank
and I
you.
think
Bye-bye.
Giangia has a good suggestion that we should choose today the beer garden as the main venue for going there, so that people don't spread around and remain lonely in too many different venues. So for those of you who are interested in gathering a little bit, focus on the beer garden environment. Hope to see you there soon.
Cool.